Let us start today's discussion about spin quantum number and Bohr Magneton. It is under atomic spectra, lecture number 5, and I am Dr. Bhattacharyya. What we have seen from our earlier lecture that for principal quantum number n equal to 1, L0, termed as S or sharp level, for n equal to 2, L is 0 and 1, 0 designates sub-energy level S, and 1 stands for P, which is known as the principal. When n equal to 3, L equal to 0, 1, 2, 0 stands for S, 1 stands for P, and 2 stands for D, which is termed as diffuse. Similarly, for n equal to 4, L is 0, 1, 2, 3, and 0 as usually designates sub-energy level S, 1 designates sub-energy level P, 2 for D, and 3 for F, which is termed as the fundamental, and so on. At a glance, we can see that all the spectroscopic terms is termed as L equal to 0, 1, 2, 3 as the SPDF. And L is known as orbital quantum number. Now the question arises, if we look for n equal to 2, when the principal quantum number n equal to 2, then L equal to 0 and 1, fine. Here S and P, two sub-energy levels are there within n equal to 2. Later on we will see that maximum capacity of S sub-energy level, it is 2, and maximum that of P, it is 6. Now the question arises, when n equal to 2 and L equal to 1, it is definitely representing the sub-energy level P. But if the maximum capacity is 6 and if 6 electrons are there, then what is the method to identify all the 6 electrons at a time? Because all the 6 electrons, they are lying for n equal to 2, and all the 6 electrons in the P level, they are lying with the designation L equal to 1. So how we can distinguish the electrons from one to another? So here we will start to discuss about the another quantum number, spin quantum number. Before that, let us see few things. That is, when an electron, it will revolve through a particular orbit around the nucleus, it will possess one angular momentum. And due to that angular momentum, or due to its own motion, there is a magnetic moment is associated. And the orbital angular momentum of electron, if we write as the P, and it is an orbital, so designated by PL with the vector sign, then we know it is r cross mv, where r is the radius vector and v is the linear velocity, which is directed tangentially of its path. And the direction of the PL vector is perpendicular to the plane of the orbit. And the magnitude of that orbital angular momentum, it is mvr or mrv. Now, if we check that the quantity mrv, what we have seen here, it must be quantized, because the previous lectures we have seen that from the Wilson-Sommerfeld model, that every angular momentum or the azimuthal momentum or whatever we have distinguished or we have noted, it should be quantized with the order of h by 2 pi. So some numerical value which will be the weightage factor of h by 2 pi. So under the same reason, that PL should be some numerical value of h by 2 pi, and that numerical value for PL, it is L, that is known as the orbital quantum number. Now, a circulating electron is equivalent to a current in a loop. So when the loop we will have, it would give a rise to a magnetic dipole moment, which is known as I into A, product of the current of the moving electron and the area of the loop through which it is orbiting. Now, if I is the current strength and A is the area of the loop, the figure is like that. It is that closed loop, the elliptical path, the electron position A, the next time at the B, and the angular gap is d theta. Then if OA be the radius vector r, then what is the distance traversed? That is to the arc of that curve. It is AB. So we can write for the elliptical orbit, if the A is the initial position, B is the final position, d theta is the incremental angular distance, and OA is the radius vector, then from this picture we can write the area traversed by the electron for this particular triangle. It is the triangle OAB. It is half into base into height. Base is r d theta, height is r. So incremental area is half into r d theta into r. Now this electron, it will revolve through the nucleus. So in this way the number of this incremental area are there from point to point as the position of the electron gets changed. So if you want to have the total area, obviously we will sum up, that is we will integrate. So the integration will be for a complete rotation under the time, total time, which is the time period, capital T. So it is the time period, we will integrate that quantity with the limit 0 to t. And just rearranging the quantity d theta dt into dt. And we can write down PL, which is termed as the MRV or MR square omega. It is nothing but MR square d theta dt. I can safely replace it here. So d theta dt is PL by MR square. So ultimately under the integration, this total area comes out as half into PL by M into T. Now just putting the current, because we have that aim to find out what is the magnetic moment of the closed loop. It is mu L. It is A into I. So just taking the product, current means charge by time, electronic charge E. We get mu L as E by twice M into PL. And I know the PL value is LH by 2 pi. So nextly, we can write finally mu L equal to E by twice M into PL, that is L into EH by 4 pi M. Now look, in EH by 4 pi M, every constant has its particular value. E is electronic charge, H is Planck's constant, M is rest mass, and 4 pi is constant. The full constant is termed as mu B, and that mu B is termed as Bohr Magneton. So we will know from today that is mu B equal to EH by 4 pi M or EH cross by twice M. The value is 9.274 into 10 to the power minus 24 joule per Tesla. As E is negative, mu L is oppositely directed to that of PL. That convention will carry on. And the ratio, very important ratio, that is the ratio of the mu L to PL. If I divide the magnetic moment with the angular momentum, here both are the orbital, then the ratio comes as E by twice L. So what we get, that mu L by PL, which is E by twice M, that quantity is known as a gyromagnetic ratio. So from today we will remember that quantity mu L by PL as gyromagnetic ratio. The quantity is valued as E by twice M. Now regarding this statement, that is the spin quantum number, why we need it? Because we have to discriminate each and every electron for a particular sub-energy level, and this quantum number will help us. In 1925, Goudsmit and Allenbach proposed that an electron must be looked upon as a charged sphere, spinning about its own axis, having an intrinsic or built-in angular momentum and consequently an intrinsic magnetic dipole moment. These are called spin angular momentum Ps and spin magnetic dipole moment μs. So when it will move by its own axis around its own axis, it will develop its own angular momentum of itself. It is called the intrinsic or built-in. So we shall write PL as L vector. So we will be enough mature to tackle that chapters of the atomic spectra. We will not carry on the quantity by PL, just L, capital L vector. And the spin angular momentum just by capital S vector. So actually it is a vectorial representation of quantum number, the vector model of quantum number. So when we get mu L as half into E by m LH by 2 pi that we have seen, in case of mu S, same quantity we shall write because that angular momentum will be quantized by the factor h by 2 pi and weighted by the factor s. Same thing, only the letter gets changed, L to S. And mu S, just look, here it is 2 into the rest part, it gets doubled. Why? Because it arises to the spin up or spin down condition of the electron. So we have seen the gyromagnetic ratio mu L by PL. Similarly, we can have the gyromagnetic ratio mu S by PS. So if I write down, then mu S by PS equal to 2 into mu L by PL. So gyromagnetic ratio for electron spin is twice the corresponding ratio for the electron orbital motion. If I just goes back the previous slide and we come back again to that, it is that relation. Now if I put one assignment, that can we find the magnetic moment of a single s electron? S electron means one electron which is residing in the s sub-energy level. What will be the answer? The answer comes as, we know that mu L this factor and mu S as this factor, and the answer will be mu S equal to 2 into half E by m SH by 2 pi, and later on we will see the value of S is half. Why it is half? It is experimentally proved. The name of the experiment is Stern and Gerlach. So that factor, if I put half, then check EH cross by 2m, because 2 into half cancels out. So the magnetic moment for a s electron is dependent upon the factor mu s. Now we can ask why I have not taken mu L, because for the s electron L factor is 0. Now automatically another question comes to play. So really the electron is in rest condition, it has no orbital motion. It's a very peculiar question. That is, the s electron has the s value, s electron has no L value. So we will discuss it later after having few classes over this chapter. So up to this, goodbye.